You are given a question and you are asked to consider a flat disk of radius r carrying a uniform surface charge density. The disk sits in the xy plane and the z-axis extends out from the center perpendicular to the disk, and you are asked to find the electric field at the distance z above the center of the disk. So since we are asked to find the electric field z, and we should keep in mind the shape, which is the flat circular disk with radius r. So assuming this is a flat disk, if this is a flat disk and this is the radius r, and we have the distance above the center, which is z, and we are asked to calculate the electric field at this point. So the electric field E, this is EY, and we have here to be theta and this to be r, and let me use here to be h instead, and this is h, here is r, indicating the radius. So, and h is equal to the square root of r squared plus h squared, plus z squared. So r squared plus z squared, using the Pythagoras theorem. So for us to calculate the electric field in this, we have the electric field E is equal to K, the integral of dq divided by h squared. So, and this is equal to E, K is 1 over 4 pi epsilon naught, the integral of dq will be sigma A. dq is equal to sigma dA, and A is area of a circle is equal to 4 pi r squared, area of a circle pi r squared. So the A will be equal to 2 pi r dr. So the Q will be equal to the sigma 2 pi r dr. So this is 2 pi r dr divided by h square is r square plus z square, but remember we have to resolve it in a y component, and we'll be having this to be cos theta, that is adjacent, which is c, divided by the square root of r square plus z square. So if we try to simplify this, okay, before the simplification, the center of this is 0, and up to this end is r. So we are integrating from 0 to r, and let's simplify. Then electric field E will be equal to 1 over 4 pi epsilon naught, the integral from 0 to r. Okay, let's take out some constants, and this will be 2 pi. Oh, there should be sigma here. 2 pi sigma r dr divided by r squared plus z squared 3 divided by 2. And this z should go out as well. Here is z. So to integrate this, we have to assume, okay, let's take the integral out. The integral from 0 to r dr divided by r squared plus z squared 3 divided by 2. To integrate this, we can say let u be equal to r squared plus z squared. So we have that du dr is equal to 2r, and this implies that dr is equal to du divided by 2r. Okay, if we decide to substitute this in the integration, we'll be having this expression to be equal to, okay, 0 to r to be equal to r. Okay, let's see if we can change the limit of integration here. So at the point where u is equal to where r is equal to 0, when r is equal to 0, we have u to be equal to z squared, and when r is equal to capital R, then we have that u is equal to big R squared plus z squared. So changing the limit of the integration, then we can write that the integral from 0 to r dr divided by r squared plus z squared 3 divided by 2 is equal to the integral from 0 from z squared to r squared plus z squared, and we assumed u to be this expression, this divided by u power 3 divided by 2, and the r is du divided by 2r. So r can cancel r, and we are left with this expression now. The integral from z squared to r squared plus z squared. If we decide to rewrite this, we'll be having u power negative 3 divided by 2. Okay, this should be 1 divided by 2 du. And this is equal to, if we integrate this expression, we'll be having 1 divided by 2 multiplied by minus u, okay, minus 2 over 1 u power half, negative half, with the limit of z squared and r squared plus z squared. So 2 can cancel 2 and we'll be left with u negative u power negative. Okay, u power negative half will be same thing as having this expression minus 1 divided by the square root of u. So, and if we substitute this, the limit of integration, then that is z square r square plus z square. So we'll be having this integration, the integral from 0 to r, r dr r square plus z square 3 divided by 2 to be equal to, okay, this should be 1 divided by square root of z square minus 1 divided by r square plus z square. So, and the square can cancel the square root, will be left with 1 divided by z square, 1 divided by z rather, and minus 1 divided by the square root of r square plus z square. So this is the integration. If we decide to substitute the integration back to this our expression, this expression where we have the electric field to be this, and we'll be having this as the electric field. That is, E is equal to 2 sigma pi z divided by 4 pi epsilon naught multiplied by 1 over z minus 1 divided by r square plus z square. So this is the electric field. So let's solve question 2. The B part of the question says we should consider the case where z is much more greater than r, and we should as well find the electric field Ez in this case by taking the limit of your general expression and give a brief physical explanation of the result you obtain. Okay, let's solve. If this is electric field, in a case where z is much greater than r, then if we decide to if this is much greater than r, we can say that z doesn't have any significance. Sorry, r doesn't have any significance. And if we decide to eliminate this r and assume everything to be z, so we'll be getting the same expression as 1 over z minus 1 over z. So in that case, everything will be 0. So to avoid this, we are going to use Taylor series expansion. If we decide to use the first approximation, we'll be having 1 plus power n is equal to 1 plus n, then the e. Rewriting this expression so that it will look like this, then I can say 1 divided by z squared plus r squared is equal to 1 divided by z. If I bring out my z, then I'll be having 1 plus r divided by z squared all to power half. So I've gotten this expression to look like this. So this will be equal to 1 divided by z into 1 minus half r squared divided by z squared. So substituting this expression in place of this in the electric field, we'll be having the electric field to be equal to E is equal to 2 sigma pi z 2 sigma pi z divided by 4 pi epsilon naught, and we have 1 divided by z minus 1 over z into 1 minus 1 over 2 r squared divided by z squared. If we decide to simplify further, we'll be having this to be E is equal to, well, let's rearrange a little. This is sigma z divided by 4 pi epsilon naught 2 pi. I have this 2 pi and 1 over 2 r squared z squared. So, and some things can cancel and we'll be left with E is equal to sigma pi r squared divided by 4 pi epsilon naught. This should be z cubed because z multiplied by z squared will be z cubed and will be z squared. But we know that area is equal to pi r squared, and the charge Q will be equal to sigma A. Then that means charge is sigma pi r squared. If charge is equal to sigma pi r squared, then we can substitute and have our electric field to be E is equal to Q (1 over 4 pi epsilon naught Q over z squared), and this is the electric field relating to a point charge. initially what we have is this circular coil, a circular disc. This is R and here is Z. This is what we have before. So, and the case where Z is much greater than R. So for the fact this increases, then the radius will become smaller. It will get to a point where this whole thing will be looking like a point charge, and that's why we have the electric field to be that of a point charge in the case where Z is much greater than R. So let's solve the last part, which is question C. For question C, we have, we are now asked to consider the alternative limit where R tends to infinity and determine the electric field EZ in this case. For R tends to infinity, and we have our electric field to be sigma Z divided by 4 pi epsilon naught 2 pi 1 minus Z minus 1 divided by square root of Z square plus R square. As R tends to infinity, this expression 1 divided by the square root of Z square plus R square will be equal to 0. So in this case, our electric field can be written as E is equal to sigma Z divided by 4 pi epsilon naught 2 pi multiplied by 1 over Z. So in this case, some things can cancel. We have Z can cancel Z, 2 pi, we cancel 2 pi, and we are left with E is equal to sigma, here is 2 pi, here is 2 rather, and sigma divided by 2 epsilon naught. So this is the electric field.